Welcome to qnawire.
So we have a system here. Now we have steam entering a turbine, and we have a boil. Let's see here. Let me pull up the problem here so I can make sure I tell you right. So yeah, we have a boiler here, a turbine, condenser, pump, a mixing chamber, a second pump, and then this is a process heater. So this is kind of the new thing with the cogeneration plant. So in this case, what you're doing is, let me see, let me actually put some energy flow. So here we're taking energy out of the condenser, taking out of the turbine, and taking out of the process heater, and we're putting energy into the boiler. So the idea here is that this energy is getting dumped into the environment, so it's being wasted. This is mechanical energy that we're assuming to be converting into electrical energy, probably um, running a generator. And then this is energy the heat energy that we're dumping into something where we want it. So we're utilizing this to heat a building or heat something. So it's a cogeneration plant is a lot like a regenerative cycle or a reheat cycle where you're using some of this heat. In that case, you're using some of this heat to then help with the boiler. Um, but now you're using it for other purposes, whatever it might be. So I don't know if they actually gave us a use for this. Let's see, a string condensed and the tower produced and the utilization factor. Now, it basically just says that it doesn't tell us what we're using this process heater to heat. But again, something here is being used. So we're extracting some of the heat that we would normally be just dumping into a cold reservoir here. So doing the analysis, let's see here, we have 7 megapascals, and then we bleed some off at 1.2 megapascals, and the exit of the turbine is 110 kilopascals. You have a total mass flow rate into the turbine of 55 kilograms per second, and 1/4 of it is bled off at 7 here. So we have a quarter of it flowing off here, and then 3/4 of it going into the finishing its way through the turbine and going into the condenser, and then being pumped up to a pressure here to this pressure so that they can mix, and then finally being pumped up to the boiler pressure and then coming back around. So this would be like some kind of radiator or heat exchanger here where you're actually using the heat. So we can figure out kind of the normal process here. Um, Enthalpy coming into the pump, specific volume coming into the pump, work by the pump, okay, from this stuff and the change in pressure. And then the enthalpy coming out of the pump, again, is this plus this. And now into the mixing chamber, again, we're assuming that this is a condensed, 3 is a condensed, or is a saturated liquid. And so we have the enthalpy for a saturated liquid at 1.2 megapascals, it's this value. So that's at 3. Now, if we look at the mixing chamber here, do a control volume around it and an energy balance on it, we have the enthalpy flowing out and then the enthalpy flowing in. And that must be, they must be equal. And so now we see we have H3, we have H4, no, we have H2 and H3. M4 we know is the same, or M4 is the same as M6, right? M2 is 3/4 of M6, right? Because that's coming through here. And then M3 is 1/4 of M6. So, and we know M6, so we know everything in here except for H4. So we can find H4, and that's 344.3 kilojoules per kilogram. Now, let's look at this pump. We know, again, we're assuming that we have a saturated liquid coming in here. We know the enthalpy now, so we can look, if we can figure out the specific volume for a saturated liquid with this enthalpy, and that turns out to be this value here, so a little bit higher than here, obviously, because it's hotter. And then we can figure out with this, we can end up change in pressure across the pump, we can figure out what the work by this pump is. And with this and the enthalpy at 4, we can figure out the enthalpy at 5 because it's just the sum of these two because of an energy balance around the pump. I should also, I guess I should be more clear here. We're putting work into the pump also. So that's kind of the energy flow: in, out, out, out. This is basically, this is where we're really putting most of the energy in. So then, let's see here. At 6, we have a pressure and a temperature. So we were told that the temperature of the turbine inlet was 500 degrees C. So we can get the enthalpy and the entropy. We're told that, again, that we've already used that the pumps were isentropic, but we also have that the turbine is isentropic. So we know that the entropy at 7 is the same as at 6, and we know the pressure at 7, so we can get the enthalpy at 7. And then the entropy at 8 is also the same as that at 6, and we know the pressure at 8. So we can get, this winds up in two-phase region, so we can get the quality factor and then the enthalpy at 8. And now we have the enthalpy at all of our inlets and outlets of all of our devices. So we can start doing some energy balances. And so we look at the turbine here, and the power out of the turbine is the mass flow rate at 6 times, let's see here, that is the enthalpy, let's see here, is that right? Yeah. So the enthalpy times the enthalpy between 6 and 7, right? And then plus the mass flow rate at 8, plus the enthalpy between 7 and 8. So I've divided this up in a little bit of a strange way. You could basically do it again because you're bleeding some off and then you're having some over here. So again, this is so the 8 is m dot 8 is just three quarters of m dot 6. So let's see here. So yeah, from 6 to 7 we have the full flow, right? And from 7 to 8, we have 3 quarters of it. So that's why we have this here split. And so then we wind up with 54.5 megawatts out of the turbine. The rate of work, the power into the pumps, we know the specific work in each pump, and we know the mass flow rates through each pump. So we can add it all up, and we get about 208 kilowatts into the pump. And so the network is just this minus this, and so we have about 54.3 megawatts. Now we have a heat transfer. We can figure out the heat transfer in the boiler. Oh no, through the process heater. So this is the heat that we're utilizing. So this is this heat here. It's coming out during this process here. And so that's the mass flow rate through the boiler times the enthalpy change across the boiler. And that winds up being about 31.4 megawatts. So we're getting a lot of heat out of here. We haven't figured out what we're putting in yet. So again, we're utilizing, about 86 megawatts of the energy that we're putting in. And so finally, we can look at the heat that we're putting in. And that winds up being about 170 megawatts. So that's the mass flow rate through the boiler times the difference in enthalpy across the boiler. So we have 170 megawatts we're putting in as heat by presumably burning something. So then we can figure out the utilization. So what we're using is the power, the net power. Again, that would be the power out of the turbine, and assuming the turbine is also running the pumps, that would the net power out of this minus these two things. And then we're also using this. And if we add all those up, we get a value for the utilized work, and divided by the heat, the utilized power divided by the power that we're putting in, and we get roughly 50%. So we're utilizing about 50% of the energy that we're putting into the system.